In this video, I'm going to talk about a theorem that Griffiths uses, where he looks for what he calls the good in quotes states, where the good states are those that are degenerate in the unperturbed system, but lose their degeneracy when the system is perturbed. We need these states before we can perturb the system, and so the methods of the last video can work. But there is another way that exploits the symmetry to make it easier. And so once we use this method, then we can actually just use the non-degenerate perturbation theory, which is a bit simpler on the states that we can find. And so, like I said, we will be using the symmetry to make it easier. So we can define a Hermitian operator, uppercase lambda, which commutes with our ideal Hamiltonian and our perturbation Hamiltonian here. And so it commutes with both of those. And so we have two degenerate eigenfunctions of our ideal Hamiltonian here, which is this green psi sub A and this pink psi sub B, where these two states are also eigenfunctions of our uppercase lambda. Then these two states are the good eigenstates, which we can use in our non-degenerate perturbation theory. This works since our real Hamiltonian, which is the ideal plus our perturbed Hamiltonian here, and this uppercase lambda commute, they therefore have simultaneous eigenstates. And so if we act with our real Hamiltonian on our eigenstates here, we can get the energy from the Hamiltonian. We can get whatever this eigenvalue is, this gamma eigenvalue from our lambda here. And so if we take both sides of this, if we do the inner product with this psi sub A here, we get this. We can pull this gamma outside because it's just a scalar, and this uppercase lambda is Hermitian, and so we can sort of pull that and act it just on this bra vector here because it's Hermitian, then its complex conjugate is equal, well, its transpose complex conjugate is equal to just the regular non-transpose complex conjugate version of the uppercase lambda. So we can act it on either one of these, the bra or the ket here. And so with the lambda acting on this psi sub A here, we get some value mu, which is the complex conjugate of mu here. So we have this mu times this bracket here equals this gamma times this bracket here. We can subtract the mu part from both sides, so we get this equal to 0. And we are saying that the eigenvalue has to be real, and so the complex conjugate of it is just equal to the mu. And so we can then factor out the gamma minus mu here times this bracket here and have that equal to 0. And so this will be equal to 0, which is, sort of the trivial solution unless we have that gamma equals mu. And the same will go for our psi sub B here, where now I'm using gamma minus mu here rather than, or nu here rather than mu. And we know that our good state, so this psi sub gamma here, is a linear combination of our psi sub A and psi sub B here, where if gamma equals mu, then the beta on here will be equal to 0, and if gamma equals nu, then the beta, or the alpha rather, will be 0 on here. So then we can use non-degenerate perturbation theory on our good states. And so this was a bit abstract, so if we use an example here, so if we use our Hamiltonians from an earlier video where we have this ideal Hamiltonian here for a two-dimensional harmonic oscillator, and then we have our perturbation here, which is a function of x times y. And so a couple videos ago, remember, that gave us that sort of oval-shaped bowl function when we had this here, when we had this perturbation. So we can exploit the symmetry. The unperturbed state has continuous symmetry under rotations, because remember that was just that bowl that was perfectly circular. It was with the perturbation that gave us the oval shape. And so that has discrete symmetry, needing to be rotated integer multiples of pi radians. Since that oval, you have to rotate it exactly 180 degrees in order to get it back superimposed on itself. And so as such, our Hamiltonian is, which is this h here, will equal our ideal plus our perturbation here will have the lowest symmetry. So the highest symmetry is the one that's continuous. The other one has the pi radian symmetry, discrete symmetry. So that's the lowest symmetry. And so that's what we will use here. So if we apply our rotations pi with some operator r of pi here, what we get is just both of these having a -1 eigenvalue, and so these are degenerate under this rotation here. We can instead do a reflection about the 45-degree angle operator, which just interchanges the x and y here. And so when we acted on our psi sub a, we just get the psi sub b, and when we acted on the psi sub b, we get the psi sub a, which means they're not eigenstates of our sigma here, but a linear combination of them is our eigenstates of this sigma here, this reflection operator. So we can see that we end up with this linear combination right here. So this plus or minus, and that's plus or minus psi sub a plus psi sub b. And so when we act our reflection operator on this, we just get the same thing back right here. And so this is an eigenvector of our reflection here, meaning that we have eigenvalues because we have this here, but with this plus or minus on it now, meaning that the plus and minus 1 for this sigma, this reflection operator, and we know that this reflection operator commutes with both the ideal and the perturbed Hamiltonian here, since interchanging x and y doesn't change the Hamiltonian. And therefore, with this state right here, we could then use our non-degenerate perturbation theory. And so, that's just a way that makes it easier for us. And so, I mean, this video is essentially just showing that there is oftentimes an easier way to find these degenerate states right here, which we can then use non-degenerate perturbation theory on, since we know which one of these states will end up becoming sort of, the higher energy one, and which one will end up being the lower energy one once the perturbations sort of lift the degeneracy from it. But anyway, I hope you found this video helpful. In the next couple videos, I will be looking at some ways of using perturbation theory. So I'll be looking at the next video at the fine structure of hydrogen, using the relativistic correction and then spin orbit coupling, which will probably be in the video after that. But so anyway, I will be looking at some uses of these perturbation theories. Probably look at the Zeeman effect after that, and so yeah, there will be a few types of ways that we can actually use this perturbation theory. Then after that, I will be looking at the variational principle. But anyway, I don't want to get too ahead of myself. I hope you found this video useful, and I'll see you in the next one.